Today we're going to be going over how to determine if a molecule is either polar or nonpolar. And to do that, we're going to go through these 5 molecules, and we're going to first do the Lewis structures, and then from there we'll assign partial negative charges and dipole directions. Starting off with SO3, we're going to put the least electronegative ion in the middle. That's S, because it's, look here, O has a stronger pull on electrons than S does. So it's just going to go in the middle. I have a bond, O, very, very basic. I haven't even counted electrons yet. To do that, all you're going to do is you're going to look on the periodic table and count the valence. So that's 6. And that's for that. That gives us 24 total electrons to work with. And so what we're going to do is, before I even start, I am going to take into account that S is on the 3rd row from the top, and I know that in that column and beyond or below, they are octet violators. So I already know that S, giving all of these, S will lack electrons. So I'm going to start backwards and use what I know about how O's like to hold atoms and work from there. So I know that O's, being in 1, 2, 3, 4, 3, 2, they prefer to have 2 sets of bonding electrons, and then the rest non-bonding. So I'm gonna actually put the rest of the bonding electrons here, and I've already used up 2, 4, 6, 8, 10, 12, and I'm gonna assign the other sets to each of these. Yep, that's right. S, like I said, S can hold more than 8 electrons because it is an octet violator and it has that 3D subshell. Now, next up, you want to assign partial charges. And since I said from the beginning that it is the least electronegative, atoms are going to move, or electrons are going to move outward toward the O's. So it's going to look like that. And in doing that, we know the dipole directions, because it's going to be as such and as such. Yep. And then to know the actual partial negative charges, all you do is you take the number of valence electrons, subtract it from the number of bonding electrons, like the number of the actual bonds, subtracted by the total number of non-bonding electrons. So we have 6 minus 1, 2, minus 1, 2, 3, 4. And it gives us 0 charge. We have here, we have 0, 0. Then S, that is, I think it's 7, 1, 2, 3, 4, 5, 6. That is also 6. So we have 6 minus 1, 2, 3, 4, 5, 6. That is also 0. Perfect. All that does is that validates what we know. So if we look at the number of domains, 1, 2, 3, there are 3. So it's a trig planar. And there's no non-bonding, so there's no different molecular geometry. And we know that whenever you have something, let's say, okay, we have a SO and O like that. If they're all pulling in the same directions, this is actually not how they look. They're actually going to look like this. And since they're pulling up and then these are pulling out, these actually all cancel because they're the same distance. So whenever they all cancel, it becomes, or we note it as a non-polar molecule. Pretty neat. Sweet. Okay, moving on. We have OF2. Now, I already did the Lewis structure, but I'll be able to assign partial negatives. So OF here, we did is we assigned the electrons to each of them. F's like to hold 1, and then the rest out on the outside. O is like to hold 2, and then the rest on the outside. And then to apply partial negatives, we know that F is the most electronegative atom, so it'll demand more electrons. It'll look like that. And then we know that the bond dipoles are going to go this way because they follow the trend of the poles with the negative sign. And then doing the partial negative, we have 7 valence minus 1 minus 6. That gives us 0. It'll be 0 over here. And then we have 6 minus 2 minus 4. That gives 0. Sweet. So we already have that set. Now we just have to count the domains and see what it behaves like. I have 1, 2, 3, 4 domains, so that's going to be tetrahedral. But because 2 are non-bonding, we know that it's going to actually be a bent molecule. And with it being a bent molecule, we'll be able to say that it's going to look like that. And if we do know from doing that it is a bent molecule, then we know that it is polar because they're going to be pulling in this downward general direction rather than in other directions. Next we have BeCl2. I assigned the electrons. B likes 2, Cl likes 1 and 6. Like we normally do, we put the least electronegative atom in the middle. And we can from that determine the dipole directions, and they're going to be the same because it's the same atom poles. And we see that it is just 2 domains, so it's going to be linear. And there's no non-bonding, so it's just linear. And all it's doing is it's pulling in a linear pattern, just like this. And since it is canceling out, we know that it's nonpolar. Next we have CCl4, very similar to the previous one. The electrons are set in place. We have 32 total valence electrons to work with, and everyone is happy because they have the number of electrons they like to have. We assign partial negatives. Yep. Sweet, and then that tells us which direction to pull in. And just to clarify for the previous one, you have 7, -1, -6, 0. BE is 2, -1, 2, it's 0, and then 0. That is how you get that. Moving back to here, we have the same thing. Cl likes to hold 7, -1, -6, 0, 0, 0, 0. And then C prefers to hold 4, so we have 4, -1, 2, 3, 4. That gives us 0 also. Now, because there are 4 domains and then there are no non-bonding electrons, we know that it's tetrahedral, and the molecular is also tetrahedral, so it's going to pull in 3 dimensions. It's going to pull this way, that way, and upwards. But because they're the same electrons, they're going to have the same bonding electron length. And then that tells us that it is nonpolar because all the electron poles cancel. And then lastly, we have ozone. Ozone is probably the most difficult because it is it does contain resonance structures. So we assign all the electrons inside of it. And then these are partial electron bonding electrons, so they're going to be about 1.5 each. And this is just a general way to talk about it. This isn't like actually what happens. This is just a visualization of it. And I kind of gave it away in how I drew it, but it is bent. And if we want to assign the partial like negatives, because this one is, I guess, in the center, you would see partial negatives like this. And to take away from this one, you would do 6 minus whichever one you had the most 2 on. And then, of course, you would have like 2 up here or something. So this one would come out to like plus 6 minus 1, 2, 3, 1, 2, 3. Come out to plus 1, or any of them would come out to plus 1. The other ones would be like 0 and 0, or 0 and -1. However you do it, this is the general resonance structure, and it shows us which way the bond dipoles actually pull, which is this way. And then since they do cancel in a linear pattern, but this is a bent because it isn't actually canceling as such. This isn't actually what's happening. They're actually bent because the non-bonding electrons of wherever they are, they're bending the structure like this. And we do know that a bent pattern travels in one direction rather than canceling. So it comes out that this is also polar. So in our total work done, we did SO3, if it'll get good. We discovered that this one was nonpolar, SO3, OF2 was polar, BeCl2 was nonpolar, CCl4 was nonpolar, and then O3 was polar. All right, and lastly we have O3 or ozone. This is perhaps the hardest one to work with just because it's not going to be all neat, and it does violate the octet rule because you're going to have different resonance structures. But if we assign the partial like charges, we're going to get a -1 on the outsides. And then with this one, depending on how you draw it, it's going to probably have a 0 in the middle, or it might have, negative on one side, 0, and then negative, or negative 0, just depending on how you draw it. And how we found those is we just did the number of valence electrons minus the number of bonding, where depending on how you draw it, it might be 2 minus that. But you see, this one would be for that one. It just all depends on how you draw it. Like I said, the most confusing one to work with. But depending on how you draw it, one of them is always going to be pulling more than the other one, because this isn't real. This is just like a way to better understand where they actually are in the structure. And since they're not actually like symmetrical, so if it was linear like this, it'd be canceling. But since it has a domain geometry of 3, but an actual molecular geometry and implied bent as such, we do know that it is polar, because it's not the direction of each dipole. So if we were to draw in here, it would be something like that.